In this lecture, I'd like to discuss how to solve differential equations that have discontinuous forcing functions. And the method of choice is going to be Laplace transforms. In fact, I'd say this is where Laplace transforms really start to shine. And so let's recall what is a forcing function. Well, if we have a second-order differential equation with constant coefficients, this could be modeling a mass spring system, for example, or an RLC circuit. So it could be modeling some kind of physical system. And in that case, recall that we interpret whatever this function is on the right side as an external force. So if it's zero, if it's homogeneous, then it's just a system acting on its own. If we have some function there, we can interpret it as some kind of external force. And so far, these have been, really nice continuous functions. For example, cosine or sine. But actually, what we want to do now is we will now allow this function f of t, our forcing function, to be discontinuous. So let's actually say piecewise continuous. Piecewise continuous doesn't mean continuous. It's a discontinuous function, but it might be continuous, but we're going to essentially allow things like this. So best way to describe what piecewise continuous means is just by drawing a graph of a typical piecewise continuous function. So it might look like this, and then I might jump down to this value instead. But then I'll be continuous again for a while. But then maybe here I'll jump up to this value. Okay, so it's made up of continuous pieces, but it might be discontinuous. So here's an example of a piecewise continuous function f of t. Okay. But there are, let's say, finitely many discontinuities. Okay. Okay, so how do we deal with functions like this? Well, there's this mathematician, Oliver Heaviside, and he basically introduced a really nice method for dealing with discontinuous functions like this, or piecewise continuous functions. So he introduced a way to represent piecewise continuous functions. Oliver Heaviside was a really interesting guy. He was an electrical engineer and a mathematician, but he was largely self-taught. He just read Maxwell's books and then just sort of went off on his own. Ended up discovering or even rediscovering a lot of important mathematical concepts. And several of the terms used in electrical engineering were actually were chosen by him. But here was his idea. He defined a single function u of t to be 0 or 1. And it's 0 for t less than 0, and it's 1 for t greater than 0. Let's draw a picture of that function. Okay, what does that look like? So it's 0 up until t equals 0. Here's t. And then it becomes 1. And then it's just 1 for the rest of the time. So it has a discontinuity here at t equals 0. Steps up to the value 1. And this is called, actually, the unit step function. Unit meaning it takes the value 1. Or in honor of Heaviside, this is often called the Heaviside function. Okay. And so what's the big idea here? I mean, surely people have considered this function before. So there are two big ideas. The first one is we can actually represent any piecewise continuous function just in terms of this one. Okay, just in terms of u of t. And the other big idea is that this actually has a really nice Laplace transform. But we'll get to that in a second. So first, let's just see how we can write functions in terms of this unit step function. So let's do a couple examples. So let's write the function I want to try to model a switch. So let's turn the switch on at t equals 2. So before t equals 2, we will have the value 0, and then it will become 1 at t equals 2. And then let's say at t equals 5, we'll turn it off again for t greater or equal to 5. So it's back to 0. Okay, so what does this look like? What do we want to do? We want to write this in terms of the Heaviside function, in terms of this unit step function, u of t. So can we figure out how to do that? Okay, first thing I'm going to do is just try to graph this, this function f of t. While I'm at it, I'm actually going to draw a couple more plots down here. Let's go ahead and graph f of t. So we're 0 until t equals 2. And then I'm going to put a closed circle there because then I immediately take the value 1 at t equals 2. So there's the value 1. And then I'm going to stay at 1 until t equals 5. And I'm going to put a closed circle there and an open circle down here at 0. And now I'm at 5 for the rest of the time. Or sorry, I'm at 0 for the rest of the time. Okay. Right, so you'll notice that this first part here looks a lot like our step function, but it's shifted to the right by 2. Okay. So how do I shift a function to the right by 2? Well, I just replace t with t minus 2. So I'm going to graph down here what u of t minus 2 looks like. It should just look like this first bit, right? So it's just this function shifted to the right by 2, which gives me exactly this first bit. However, this stays at 1 for all time, right? So how do I get this second bit where I drop back down to 0? Well, I probably want to involve u of t minus 5, right? This one shifted over by 5, so what does that look like? Well, it should just look like this. That's 5 for all, or that's 1 for all time. Okay, so why don't you take a second, you can pause the video if you want, to try to figure out how you can write this function here in terms of these two right here. And I'll say the answer in a second. Okay, so the way you do this is, well, we notice that this gives us the first part, right? So we just have u of t minus 2, but we don't want it to stay at the value 1 for all time. We want that to become 0 at t equals 5. And so you might have noticed I can do that by actually subtracting this one. So I'll subtract u of t minus 5. And let's just make sure this works. So for t less than 2, these are both 0. Great. For t between 2 and 5, that one becomes 1. But this one is still at 0. So I get 1 minus 0 is 1. Great. For t greater than 5, I get 1 minus 1. They're both 1. That brings me back to 0. So I get exactly the right behavior. And I just want to point out there's another notation that's often used. So so we will use the notation u c of t to mean u of t minus t. Okay. So we can actually write f as this is just a new notation. So u2 of t minus u5 of t. u2 of t just means u of t minus 2. Okay, let's do a more complicated example now. Let's try this for the function. So we'll have three regions again. So we'll start out with 1/2 t, linear function, from t equals 0 to let's say 2. Then we'll just have the function 2, the constant function 2, from t equals 2 to 3. And then for t greater or equal to 3, let's do something complicated. Let's have a parabola. So t squared plus, let's do minus actually. Let's do a t squared minus 6t plus 10. Have a certain picture in mind. Let's hope I got it somewhat correct. So, right, we have this function 1/2 t from 0 to 2. You don't have to graph this, by the way, in order to figure out how to write this in terms of u of t, but I find it helpful sometimes. Then we're going to jump to the value 2. So here's 2. And it will be 2 from 2 to 3, from t equals 2 to 3. Let me put the t values down here. Then I'll again do a closed circle. And now this one here, what does this parabola look like? So if you complete the square, it's t minus 3 squared. But t minus 3 squared is t squared minus 6t plus 9. So I need a plus 1. And completing the square is very useful for graphing quadratic functions, because this tells me I just take t squared, I move it to the right 3 and then up 1, right? So this is actually the vertex. Great. So it'll look something like that. Let's try to write this function in terms of u of t. Okay. Seems pretty complicated, but it's actually not too bad at all. Because we're going to use these kind of things. We're going to use these you can think of these as switches. So this is like a switch that turns on at t equals 2 and turns off at t equals 5. So here's what I'm going to do. I'm going to start with 1/2 t, but I'm going to multiply that by a function that's 1 between 0 and 2 and 0 otherwise. In other words, a switch like this. So I'll multiply by u0 of t minus u2 of t. Okay? So this is like a switch that turns on, so it's like an on switch at t equals, when is this turning on? At 0. And I'm subtracting u2 of t, so this is an off switch at t equals 2. That's how I think about these, at least. Okay, and that actually gives me this piece here. And because this will become 0 for t greater or equal to 2, this is not going to mess up anything else that I try to write down. So now I want the function 2, and I want to turn it on at 2, at t equals 2. And I want to turn it off at t equals 3. And this is how I do it. Okay? And then I want the parabola, so I want this one, t squared minus 6t plus 10. And I want to turn that on at 3, and then just leave it on. So there we go. That's my function f of t expressed only in terms of these Heaviside functions. Notice that I wrote it down in one line. That's really cool, right? I don't need these piecewise descriptions of the function. It's just this function right here in one line. That's going to be really useful for taking Laplace transforms also. And then finally, I'm just going to kind of clean this up a little bit. So it's 1/2 t times u0 of t, which is also just called u of t. Now I'm going to collect the u2 terms. So that will be a minus 1/2 t plus 2 times u2 of t plus Now collect the u3 terms. So I get a minus 2 u3 plus this times u3. So I actually get a t squared minus 6t plus 8, right? 10 minus 2 times u3 of t. All right, very nice. What should we do next? So hopefully you're convinced now that you can take any piecewise function and write it just in terms of these step functions. And this is how you do it. Let's talk about the Laplace transform. Laplace transform. Of this step function, uc of t. Okay, so what is the Laplace transform? Well, I mentioned this. It's very nice. Let's try to calculate it. So the Laplace transform of uc of t is, by definition, what is it? It's the integral from 0 to infinity of e to the minus st times uc of t dt. Okay, what is this? Well, let's think about uc of t. uc of t is the function. Well, yeah, what is it? It's 0 when t is less than c, and it's 1 when t is greater or equal to c. And so when t is less than c, this is 0. This whole integral is just 0, right? This whole integrand here. So I can actually start at c instead of 0. So I'm going to do that. I have c to infinity of e to the minus st times uc of t, but if t is greater than c, that's just 1. So I don't even need to write uc of t. It's just e to the minus st times 1 dt. And you could do this integral directly, but I'm going to actually do something that I think I can generalize a bit in the next example. So I'm going to try to switch variables so this integral starts at 0 instead of c. So how do I do that? Well, instead of t, I'll subtract t. I'll subtract c off of my old variable. So I'll call that tau. Tau is going to be t minus c. D tau is just dt. Right, that's just a constant, goes away. Which means I'm now integrating from 0 to infinity. Well, technically it's infinity minus c, but that's still infinity. And now what does this become? It's e to the minus st. T is tau plus c times 1 d tau. Well, this is e to the minus s tau times e to the minus sc. E to the minus sc is just a constant, right? With respect to tau, at least, my variable of integration. So I can pull that out. So e to the minus, minus cs. And then I'm left with, what? I'm left with this. D tau. And again, I can do this integral out if I want. But another thing you can do is view this as a Laplace transform. Right? This is the Laplace transform. This integral right here is the Laplace transform of the function 1. Right? E to the minus st times some function there, dt, is the Laplace transform of that function. Here it's just 1. Laplace transform of 1 is just 1 over s. So I get e to the minus cs over s. So that's a pretty nice formula. The Laplace transform of, let's actually write this down. Let's write it in our notebook, actually. So we have our notebook of Laplace transforms. Notice I put in the formulas from last time there. Laplace transform of a derivative of a function. So those are really useful. Okay, so what do we have? We have the Laplace transform of the step function uc of t. And we just found that that is e to the minus cs over s. Okay. a special case of this. So here's our formula. Should we box this here? We'll be using this one a lot. A special case of this is, what if c equals 0? So just u of t, right? Just the step function u of t. What is the Laplace transform of that? Well, it's just 1 over s. But wait a second. We've already seen a function with a Laplace transform of 1 over s, right? That's the function. That's just the function 1, right? The function 1 has a Laplace transform of 1 over s. So what's going on here? I said that the Laplace transform was essentially unique, and I mean we're relying on that in order to use this method to solve differential equations, right? And so here's what's going on. This is actually not a surprise. If you have, I'm going to draw a few functions here. So let's say I have a function like this. And then let's say I have another function that looks the same here, but then it goes up here, let's say. Or I have another function that looks the same here, and then it looks like that. What can we say about these three functions? They all have the same Laplace transform. So these all have the same Laplace transform. Why is that? It's because the Laplace transform ignores anything less than 0, right? It only integrates our function times e to the minus st from 0 to infinity. And so in terms of the Laplace transform, the function u of t and the function 1 are indistinguishable. And that's because they have the same values for t greater or equal to 0. Okay? So that's really the sense in which the Laplace transform is unique. Okay? Okay. Even so, we can still have some discontinuities here. So for example, this red one could look like the blue one, and maybe have a point up here instead. And those would still have the same Laplace transform, because integrals don't really care about what's happening at a discrete set of points like that. You can have a different value at one point, and the integral will still be the same. Okay. Next, what about the Laplace transform of our step function uc of t times some function f of t, let's say, right? Because look back at our examples. This function f of t we could write in terms of the step functions, but it's, for example, u2 of t times this function, and we want to know how to take the Laplace transform of something like this. So let's see if we can get a formula for this. And it turns out we can't really hope to get anything nice in terms of, the Laplace transform of f of t alone. And the reason is because this is not actually the most natural thing to consider. So it's more natural to consider this L of uc of t times f of, not f of t, but f of t minus c. Let me explain why. So let's say we have, I'm going to draw a couple plots again. So okay. Oops. Okay. Let's say we have some function f of t. Maybe it looks like this. Okay, here's my f of t. Okay, there are two things we can consider. We can turn on this function f of t at c, And here's what that looks like. So UC of t, let's say c is just this point here. UC of t is 0 up until t equals c, and then it becomes 1. So I just get 1 times f of t, then I just get f of t. But until that, I get 0, right? Because it's 0 times f of t. And now all of a sudden I jump up here, but I don't retain this information from the beginning of the function. I just start right here. So it's going to actually jump up to just that part here, and then it will go down, just like my f did. Okay. What about UC of t times f of t minus c, like that? What does this do? Again, it's 0 up until t equals c. Okay, but then what is going to happen at t equals c? I have the graph of not f of t, but f of t minus c. So it's this shifted over exactly the right amount to sort of start at t equals c. So it's going to look something like this. Okay. Okay, and so if we take the Laplace transform of this, it's very hopeful that we can get some formula in terms of f of t, because we have all of the information of f of t right there. Whereas in this picture, we lose some information. So we're more likely to get a formula for something like this. And you'll see again why that is when we actually try to get this formula. So it's L of UC of t times f of t minus c. Just by definition, that's integral e to the st times UC of t times f of t minus c dt, which is integral from c to infinity, right? I can start at c using the same trick as above. And now UC of t is just the function 1, so it's just e to the minus st times f of t minus c. And now look what happens when I change variables. So again, I'm going to subtract c off my t values, so I'll define a new variable tau. Again, d tau is dt. T will be tau plus c. That came in useful last time. So my new limits are, so I just want to make sure you understand like what's going on with the limits, right? So these are t values here. So I need to find the corresponding tau values if I want to change variables, right? So that's the t value. What is the corresponding tau value? It's c minus c, which is 0. And then this one stays infinity. Now I have e to the minus s times tau plus c times f of tau d tau. Right. What is this going to be? It's going to be the integral from 0 to infinity. I can pull out the e to the minus cs, as I did last time, and I have an e to the minus s tau times f of tau d tau, which is e to the minus cs. Again, we can recognize this as a Laplace transform. It's the Laplace transform of the function f. Just e to, we've also written that as capital F of s, right? Capital F of s meaning the Laplace transform of f of t. Okay, so so the Laplace transform of the Laplace transform of UC of t times f of t minus c is this really nice formula. It's just an exponential times the Laplace transform of f. Not of f of t minus c, but of f, little f, right? Little f of t. And so this formula is actually a bit tricky to use, but I'm going to box it, and we'll do a couple examples. Let's actually add it to our book as well. So the Laplace transform of, I don't need to put in the capital L. What do we have? F of, yeah, what was this again? Okay. Let's erase that. U of UC of t times some function, f of t minus c, is e to the minus cs times f of s. And you'll notice that the formula above that we just derived is actually just a special case of this one. right? So this f of t minus c is just the function 1, okay? And so this f of s is just 1 over s in that case. But yeah, this is actually a little bit subtle. So I want to do a few examples of this. So let's use this formula to find a Laplace transform. And what I'm going to do is I'm actually not going to express my f in terms of t minus c. I'm just going to put some random function there. So let's say we have u3 of t times the function 8t plus 1. Okay. So what is this Laplace transform? Here's what I need to do. I need to write this as u3 of t times f of t minus 3. So I need to write this function. I need to write this in terms of t minus 3, not t. And so 8t plus 1, just in order to use this formula. So 8t plus 1 is 8 times t minus 3. That's what I want. But I can't change the expression. So what did I do? I subtracted a 24. It wasn't there before. So I need to add that 24 back on. So I end up with this right here. Okay? This is my original function expressed in these terms, in the terms I want for the formula. So this is f of t minus 3. Okay. What is capital F of s? That's the Laplace transform of little f of t. Not f of t minus 3, but f of t. So I need to find, if this is f of t minus 3, what's f of t? Well, I just replace t minus 3 with t. Okay. So if that's f of t minus 3, this is f of t. And then finally, what is capital F of s? It's the Laplace transform of this one here. Okay, so that's how you use the formula. So the Laplace transform of this thing here is, what is this? Laplace transform of t is 1 over s squared. So it's 8 over s squared plus 25 over s. This right here is capital F of s. Okay, so that's what I put there. Okay. So the Laplace transform of my original function, u3 of t, times, I'll just make it very clear, I'll write this in this form. So I have times 8t minus 3 plus 25, okay. That Laplace transform is e to the minus cs, I can definitely write out that part, so that's e to the minus 3s, times capital F of s, meaning the Laplace transform of f of t. So now I need to replace the t minus 3 with t, then take the Laplace transform of that like I did over here, and so it's actually going to look like this. Okay. So that's my Laplace transform right there. So again, yeah, this formula is a bit tricky to use, but very useful. I want to do another example with it. So let's do an example. Let's find an inverse Laplace transform. Okay, so let's find another example. Let's find the what should we do? The inverse Laplace transform of e to the minus 4s over s plus 2 squared. I just want to point out also, whenever you see an exponential in the s domain, that's a sign that there's one of these functions, right, in the t domain. There's some discontinuity. Okay, let's do this inverse Laplace transform. Well, let's go to our table. We see an exponential, right? These are the only two so far that involve exponentials. And this is the more general one. So we're going to use this one. So the inverse Laplace transform of this is that. So let me write that down. This is just from our table. The inverse Laplace transform of e to the minus cs times capital F of s is uc of t times little f of t minus c. Okay, so what do we do here? Let's rewrite this as e to the minus 4s, so clearly c is going to be 4 here, times some function capital F of s. And let's go through step at a time, just like before. So what is capital F of s? It's this, right? So this is capital F of s. Let's go backwards. We need little f of t minus c. First of all, what's little f of t? So this is, I'm going to write it down in a second. What is little f of t is the inverse Laplace transform of this one. So I'm going to use this formula here. Okay. So what is a? A is minus 2, right? So and n is 1, which gives me exactly what I need in the numerator there. So I'm going to get t. Inverse Laplace transform of this thing right here is t times e to the minus 2t. Okay. I don't want f of t though. I want f of t minus c. So I now need to replace the t's with t minus c. And what is c? C is 4. So finally, t minus 4 times e to the negative 2 times t minus 4. This one here is f of t minus c. Okay. And so now I can just write my answer. What is the inverse Laplace transform of this? It is uc of t, don't forget that part, it's u4 of t, times f of t minus c. We worked out that as this right here, t minus 4 times e to the minus 2 times t minus 4. Okay. So that's how you work with that formula. You just have to go slowly and carefully and do one step at a time. Okay. I think we're ready to try a differential equation. So let's solve a differential equation. Okay, so this will be our problem. Let's say we have a series RLC circuit. These step functions, the Heaviside functions, were originally developed to study circuits. Heaviside was an electrical engineer after all. So let's do an example with an RLC circuit. So I need to tell you what L, R, and C are. So L is going to be 1, R is going to be 2, and C is going to be 0.2. Okay, and let's suppose that the initial charge, Q of 0, and actually the initial current, Q prime of 0, are both 0. Okay. And then at time t equals 0, I could have chosen different numbers there, but I'm worried that, so I think this is already going to get pretty complicated, and I don't want to make the first example needlessly complicated. So what's going to happen at time t equals 0? We're actually going to switch on a battery. So a 5-volt battery is switched on. There's our external force there, external voltage. And then at time, let's wait a few seconds maybe, so time t equals 7, we'll switch the battery off. It's switched off. Okay, let's solve the differential equation. So let's find what do we mean by solve the differential equation. So we want to find the charge in the circuit at any time t. Okay. And let's also recall what our differential equation is for the RLC series circuit. It's L times Q double prime plus R times Q prime plus 1 over c times q. And that's going to equal, what do we put on this side? That's the external voltage, v of t, which is this function that's being described here. So first of all, yeah, what is v of t? Okay. Well, we want it to be 5 from 0 to 7. And then 0 after that. Okay. We could also say it's 0 when t is less than or equal to 0, but actually we don't care about, remember, Laplace transform doesn't care about what happens less than 0. So let's try to write this in terms of our Heaviside function, our unit step function. So what is this function here? Well, this is, so v of t is, it's 5 times, we're going to turn on the switch at 0, so u0 of t, minus u7 of t. So this is my switch, it's turning on at t equals 0, and it's turning off at t equals 7, and the value is 5, the constant function 5. Okay. Great, so let's write our differential equation. So we have q double prime, right, because L is 1, plus 2 times q prime, plus 1 over c, 1 over 0.2 is just 5, 5q, and that's going to equal this, 5 times u0 of t minus u7 of t. Okay, great. What do we do now? We take the Laplace transform. And we get, remember how we deal with the derivatives. So the Laplace transform of q double prime, you can express just in terms of the Laplace transform of q. It's s squared times L of q minus s times q of 0. These were the formulas we got last time. Minus q prime of 0. And then same here, Laplace transform of q prime. Notice I'm using linearity also. Is s times the Laplace transform of q minus q of 0 plus 5 times the Laplace transform of q. And what do we get on this side? Well, the Laplace transform of, it was 5 times, yeah, the Laplace transform of this. Laplace transform of u0 is 1 over s. Ooh, I have to be careful with these 5s. I don't want them to look like s's, so I'll make them very sharp at the top. So it's a 5. And then the Laplace transform of u7 of t, remember what that formula was? That was just this one. It's e to the minus 7s over s. So we have minus e to the minus 7s over s. Okay, q0 and q prime of 0 are both 0, so these terms go away actually. That one goes away. And what are we left with? We're left with s squared plus 2s plus 5 times L of q equals 5 times, let's see, do I want to rewrite this? Maybe I'll factor out that s. And I have 1 minus e to the minus 7s in here. So what is L of q? L of q is, remember, q is our solution to the initial value problem, so we want to solve for L of q. And we get 5 times 1 minus e to the minus 7s. This is in the numerator. And then in the denominator, we have s times s squared plus 2s plus 5. A 5. Okay, and this was basically solving the differential equation, right? We solved for the Laplace transform, at least, of our solution. And now to get our solution, we need to take the inverse Laplace transform of this function here. This function is a mess, though. So we'll clearly need to use some of these formulas we got today, right? Because those are the only ones that involve this exponential. But what I want to do first is, and this is what I would recommend here. So we want to also use partial fractions to split this fraction into two simpler ones. But we don't want to do partial fractions with these exponentials. So I actually we'll move this piece outside. Okay, so I'll rewrite this as 1 minus e to the minus 7s times 5 over s times s squared plus 2s plus 5. I'm going to rewrite this one using partial fractions. So how do we do that? If you feel really comfortable with partial fractions, feel free to skip ahead a few minutes. And the idea is we want something over s and something over s squared plus 2s plus 5. A over s, what do I put in the numerator here? I have a quadratic in the denominator, so I need a bs plus c. I need a linear function in the numerator. If I just had b, then I would not be guaranteed to be able to get this function here. Okay. Yeah, I might not be able to choose a and b so that these add up to 5 over this. Let's find a common denominator. So I need to multiply this one by s squared plus 2s plus 5 over itself, and I need to multiply this one by s over s. And then my denominator becomes this, so I'll just compare the numerators. And so I have s squared terms. We'll do this the same way we always do, right? So we have s squared terms. Let's look at the s squared terms. A s squared plus bs squared has to equal 0s squared on that side, right? So a plus b is 0. Where my s terms, so 2as plus cs has to equal 0s. I don't have any s terms on that side. So the coefficients have to be the same. And then my constant terms, I have 5a, and that's my only constant term over there. That just has to equal 5. Oh, that's really nice. That just tells me a is 1, b is -1 from this first equation, and c is -2 from the second equation. Okay, very nice. So, where are we? So, this is our function. This is a Laplace transform of our solution. So I'm just going to rewrite that. 1 minus e to the minus 7s. But now I can rewrite this fraction as as a sum of two simpler fractions. So it's 1 over s plus minus s minus 2 over s squared plus 2s plus 5. That's what we just found. Okay. We know the Laplace transform of 1 over s. We don't know the Laplace transform of this right away. And notice we still have to multiply by this bit. So we'll have to worry about how to deal with this in a second. But before we do that, I just want to rewrite this piece here in a typical way that we've been doing. So how do I do this? So I have minus s minus 2. I will complete this square in the denominator, because this cannot be factored over the real numbers at least. What is it? It's s plus 1 squared plus 4. And now what I want to do, so remember, this is looking a lot like these two, right? The exponential times the cosine and the sine. But for the cosine, I need s minus a, exactly that right there. Right? And the other one I need the constant b. And so remember what I have to do now is I need to rewrite this numerator in terms of s plus 1. So I'm going to just put in an s plus 1. Okay. But what did I do? I added a -1 that wasn't there before, so I need to add 1 to compensate, and then I still have the minus 2 there. And this is all over s plus 1 squared plus 4. And why am I doing this? So I can now split this apart into two pieces. The first one will become the exponential times the cosine. And then the second piece will become a exponential times a sine. Okay. It's just a lot of rewriting. That's all we've been doing ever since this point. We're just trying to rewrite this in order to bash it out with the table. Okay, so let's take stock here. I have this times 1 over s plus, I'll write this out, minus s plus 1 over s plus 1 squared plus 4 plus a negative 1 over s plus 1 squared plus 4. And now I think I'm almost ready to take the inverse Laplace transform. But I think I was afraid of this, but I think I might want to multiply these all out. Because I need, yeah, let's just do it. So I need to do 1 times all of these. So 1 over s plus, what's this one? Plus negative 1 over s plus 1 squared plus 4. And now I have an e to the minus 7s over s. That will be a step function exactly, right? This is the Laplace transform of u7 of s. So we'll keep that in mind. And then I have a plus e to the minus 7s times this s plus 1 over s plus 1 squared plus 4. And then I again have a plus and minus of a minus e to the minus 7s times 1 over s plus 1 squared plus 4. Okay, now I'm definitely ready. So I'm going to take the inverse Laplace transform. And I'm just going to use our table here. Hopefully by now some of these are starting to look familiar, right? 1 over s, that is the Laplace transform of 1, right? What is this bit here? This is the exponential times the cosine. So what is a and b here? So a is negative 1, right? S minus a, and b is 2. So we actually have 1 plus a negative. Let me just write that as 1 minus. So we have 1 minus e to the at, e to the negative t, times the cosine of bt, cosine 2t. And then you're going to have minus the sine, right? But for the sine, we need that numerator to be a 2, right? Because b squared is 4, so b is 2. So we need that to be a 2 instead of a 1. Here's how I'm going to do that. I'm just going to replace that with a 2. But I need to put a 1/2 out front. Right? You've seen that idea a few times. I'm going to preemptively do that here actually. So I'm going to replace that 1 with a 2. I'm going to put a 1/2 out here. Okay, and now it's now minus 1/2 times e to the minus at times sine bt. B is 2 in our example. Sine 2t. Okay, so far that's looking pretty familiar. We've seen functions like this before. Now it's going to get pretty weird. So what do we have next? We have minus a u7 of t. It's this one here. Next, we're going to have to use these, right? So what do we have? What do we do when we have an exponential times a function like f of s here? So this right here, I'm trying to view this. I'm interpreting this as capital F of s. Okay. If that's capital F of s, what is little f of t? So let's just do this very precisely. So if this is capital F of s, then little f of t is going to be, well, we did that before, right? That's e to the minus t times cosine 2t. But that's not what's in the formula, right? The formula says little f of t minus c. So I need to replace the t's with t minus c. What is c in my example? It's that 7, right? So f of t minus 7 is e to the minus t minus 7 times cosine of 2 times t minus 7. Ooh, okay, so that's what I need to write here. So, sorry, that's just that part. And now I need to do plus this bit here. And remember also, I need a UC of t. UC of t is U7 of t times little f of t minus 7. So it's going to be this whole thing here. And this bit is going to be similar. So I need a plus U7 of t. I have that 1/2 also, times 1/2 of e to the minus t minus 7 times sine of 2 times t minus 7. Right, because this thing right here is my little f of t, but my formula tells me I need f of t minus c. So I need to replace the t's with t minus 7. Okay. All right, so this right here is q of t. Wow, so that is really nasty looking. And this lecture's already gone longer than any of the previous lectures, I think. But I want to really quickly, and I do mean quickly, I want to show you that this is actually not as nasty as it seems. In fact, we can sketch a graph of this right now. Not necessarily going to be a very accurate graph, but we can try to understand what this looks like. So what does this function q of t look like? Okay, notice that these u of 7 terms switch on at t equals 7, right? Because u of 7 is 0 up until t equals 7, and then it becomes 1. So we're just graphing this bit for the first part. And so let's say we have 1 here, and 1, 2, 3, 4, 5, 6, 7, etc. The initial value is 0, and this is just decaying oscillations, right? We're familiar with this, but we're adding a plus 1 here, so they're actually they're not going to decay to 0, they're going to sort of decay to 1, like this. Okay, so maybe it looks something like this. This part just decays to 0, but I have I'm adding 1, so it's offset by 1. What happens at t equals 7? These all turn on. This part becomes 1 at t equals 7. So I actually have a minus 1. That will cancel out with that 1. These become 1 also. And so I have these decaying oscillations. They look just like these ones, but they're shifted to the right by 7. See that? I've replaced all the t's with t minus 7. And they have the opposite sign, it looks like, right? So these start with a negative. These start with a positive. This is still going on, right? This is still going on, but this is close to 0 for, t at least 7. Either negative 7 is very small. And so basically, it's just going to look like this piece, these last two terms, which are decaying oscillations, and they'll decay to 0, actually. So something like that. Okay. So that's what the current in my, the charge in my circuit looks like. So this has been an example of solving a differential equation that has a discontinuous forcing function. And you'll notice that we were able to come up with this function by expressing our discontinuous function in terms of these step functions. And functions like this are very common in electrical engineering. So thanks for watching.